All right, so where we are, week number 9. Let's do experiment number 7 today, right? So experiment number 7, we're going to investigate the friction force. Basically, the experiment is very simple, but we're going to test it out, the friction for different surfaces, and then different type of measuring friction, 3 different simulators. So it's going to take fairly decent amount of time. I think if time remaining, we're going to go back to the previous chapter and then we'll do a couple of questions. Okay. You can download the data sheet and the lab manual as usual. Lab manual should be look like this. And the idea of the friction, everybody know by now, right? If I have object and then if I try to move the object on a surface, then the friction force will appear. So that friction force, everybody now know. We've done a couple of mini questions actually related to friction by now, right? So if I have an object right here attached to a string, and then object moving on the horizontal plane, and then other side of the string is connected to the hanger. And then if this object moving downward direction, this object is starting to move horizontally. As soon as it starting moving, this object will experience the friction force, right? So technically, let's say if this is moving with acceleration A, then if this is the tension, so the same tension appears here. This will be the object of the mass of the object B, right? So this is going to be mb times the g. And you have a gravitational force ma times the g times the normal force. And then idea of the friction, by now you should have a good idea, right? So the idea of the friction means the object going to be stay at rest initially, right? We discussed this as last week too. And then if I have a time here, and then if I apply a force and then increase the applied force, initially object will be at rest. There will be maximum force needed to break the stability, right? That maximum force needed to break the stability is actually used to find the static friction coefficient. This part right here is actually acting as a static, which means the object is at rest. That's the idea, right? Idea of the static friction. Then when the object is starting to move, this maximum force no need to be such high. It's going to be little bit lower, but remaining fixed forever. So that actually for the friction coefficient of kinetic. So the ratio between the friction force and the normal force is actually defined as the kinetic friction coefficient. If I have a maximum force needed to move the object, this will become static. If I have the force when the object is moving, then the coefficient becomes kinetic, right? So we have two type of friction coefficient. So we can actually measure those. If I have a way to measure the applied force right here to the object, then if I make this graph, then I can easily identify both of these points, right? So that actually planned for this experiment. So we're going to use a sensor, and then sensor will tell you how much force is applied to the object. Then by looking at the friction force versus time graph, we're going to identify both the static and friction forces. And then we're going to calculate the coefficient. Then we're going to do this for different type of surfaces. Now you know in a standard our in-class experiment going to be wood on the table. So that's the standard experiment. We're going to check that. And then we can check other surfaces. For example, the semi-smooth surface on the ice, right? If I have an ice surface, if I put a rubber, that will be very less friction, right? We can investigate that. And also we can test like metal on metal. How will be the friction changes if I have a two metallic surfaces touching each other? These three we're gonna take a look very in detail. And then couple of other scenarios we're gonna take a look very briefly, okay? That's the plan for the first part of the experiment. And also, you can see I can calculate by knowing this information, right? The normal force is going to be just the gravity, right? So I can easily do this calculation by knowing all of those. Also, if I rearrange this formula, friction force is equal normal time friction coefficient times the normal force. Normal force is the force of gravity. So which means if I can change the object of this mass, the mass of this object actually, by keeping the object, but we can change the mass. Okay, if it is an in-class setting, we can actually add the mass into that. But in the simulator, it's very simple, right? So if I can change the mass, I can maybe identify a data set. This may be our X, this may be Y. If I make a graph, force of gravity versus the friction force, then you can see that graph should be look like linear. And then by putting the graph into a trend line linear, by using the slope of the graph, then we can calculate slope of the graph will be actually friction coefficient. We can reinvestigate friction coefficient, not just one data point. We can change the mass of this object again and again and again, rerun the experiment again and again couple of times to see how much force is needed, and then we can investigate how that normal force and the friction force behave. If the surface remaining same, slope of the graph must be remain the same. That's the idea, because the friction is not just depending on mass or anything, it depending on the surfaces, right? So that's the idea. If it is the same type of two surfaces touching each other, friction force for that particular two surfaces should be common. However, it's difficult to find the standard values or anything because the friction coefficient is very sensitive parameter. Even if you consider wood on wood, there are different type of wood, and then there are different type of tables. There are different type of smoothness of this wood objects and the tables. Because of that, you can't really get any like standard values, but we have some idea about what this number should be. Wood on wood should be about like 0.5. That's the expected value. And the rubber on ice going to be very, very small, about like zero point 0.2 or less. And then metal on metal, depending on the type of metal, it can go all the way to like 1 or maybe 0.95, about that. So those are the numbers we know, but it's difficult to compare those things with the simulator values because we don't know what values they're using internally. Because of that, we're not gonna compare any standard values. Instead, what we're gonna do, we're gonna directly calculate by using equation. Then we'll compare that with the value we're getting from the slope of the graph. Okay, that's the plan. Question. Okay, that part one of the experiment, part A, and then after we finish part A, we're going to revisit the same kind of experiment by using a little bit of different simulation, and that will give you a better idea about how this experiment going to work in real experiment, real class setting. And then very end, we're going to take a look at the inclined plane version, but with the one object. Okay, so there's a very easy way to calculate friction coefficient with the inclined plane. That's the plan. So let's discuss that inclined plane part at the very end. Let's start with the part A. Anybody have any question? Okay, concept and theory, we've been using this now for a while in class. You have to have a good idea about this now. And the simulator link on page number 2, part number A, you can click on that simulator and you will see a page like this one. Then you can use a different language if you want, but I would suggest just keep it English. And then click on the begin button. Then that's a simulator, simple simulator, which once I use this during the class 2, this is the same exact simulator to identify the friction force. And if you take a look at the simulator, there's a start button right here. When we click that, the force applied into this force sensor right here. There's a hand on your right hand side, and inside it says vernier. This is a force sensor. So it can detect very small force down to like about 0.01 Newton. And because of that, if you, this force sensor now connected with this string to this object right here, and then what we're going to do, we're going to apply a force and then try to drag this object towards our right hand side. As we're trying to drag it, slowly increasing the force, the computer will detect the applied force and then make a graph. That graph will appear here as a function of time. Then by looking at that graph, we can easily identify what is the maximum force needed to break the stability, what is the constant friction force applied when the object moving afterward. Okay. So if we can measure those two, then we can actually calculate the friction coefficient. Then we can increase the mass of the object and then redo the experiment and then make the graph, and then we can compare the graphical number with the calculated value directly. Okay, that's the plan for the part A. So in this simulator, you can see a couple of other options. On the middle of the simulator, you can see it says object mass, and then it says 640 grams right now. And the up and down arrow, if you click the down arrow, you can see mass can changes. The smallest value going to be 100 gram. Let us start from there. Okay, if we're doing this in class, we have a cart here on the table. Usually that cart mass is about like 50 grams. You're going to add another 50 gram onto the cart, and then you start with about like 100 grams. So let click this down arrow, red down arrow, and then we'll start at about 100 grams. And then to your left hand side, very corner, it's a type of surfaces. And then right now it's a rubber on ice. But if you click on this term rubber, you can see it changes. The first word is the object, second word is the surface. Okay. Now aluminium on steel, that is a metal on metal. You click again, it will go into glass on glass. And then click again graphite on graphite. Click again rubber on concrete, and then click again, it will go into wood on lab table. So let's start from there. Reason that is our standard experiment. If you're doing this in class, that is what we actually doing. We can't do other objects and surfaces. We don't have all the surfaces and objects, but the wood on the tabletop is actually the one we actually have in class setting. Okay, so what we're going to do, we're going to slowly increase the object mass. Right now object is about 100 grams. Let us start from there and then run the experiment. Identify what is the maximum force needed to break the stability. Identify what is the force applied after object start moving. Calculate the static friction coefficient, kinetic friction coefficient, and then let's change the mass of the object. Rerun the experiment about 5 or 6 times, and then we'll make the graph. We'll compare those values. Okay, very simple experiment. In terms of calculation, it's extremely simple. Object mass, we need the standard unit SI, kilogram. Force, now you know standard unit we use in newtons, right? Maximum force, again, it's a force, unit Newton. Kinetic friction, unit Newton. Friction coefficients are just the ratio. Because of that, there's no units for the friction coefficient. Okay, just a unitless parameter. Okay, question. Okay, then let's continue. Let's start the experiment. Now we can record starting the mass of the object. We're starting 100 grams, 100 divided by 1000 to kilogram. This is going to be about like 0.1. But I'm going to keep 3 decimal places to the accuracy of the 3 significant figures, even though right now it looks like 1 sig figs. But if you increase this mass, you can see technically I can read all 3 numbers. Okay, let's consider the accuracy is 3 sig figs. figs. Okay, so let's keep that into 3 sig figs. And the normal force we can calculate easily, equal sign mass of the object multiplied by 9.81, right? So those are simple calculation. By now you should be really good on those things. We're doing this now for a while. Almost 7 weeks now, right? This is 7th experiment. So we are using the Excel sheet for all of these last 6 weeks. So you should be really good on this calculation by now. And the maximum static friction and the maximum kinetic friction needed, we can identify by looking at the graph. The graph will be automatically appears here after we run the experiment. Okay. All right, so let's continue then this function for the normal force. All we have to do is just start and then observe. Okay, that is that simple. So now all we have to do is actually measure, right? Maximum point right here. This side is static, this side is kinetic. We need to measure maximum point. Now this looks like a graph shape, right? Only this scale is given. We're not interested time at all. We're interested only force axis, y axis. So now I need to measure exactly this particular point, right? Now if I want to measure that point, this point right here, I have to identify what is this small scale is. This is like a graph sheet, like a centimeter square, millimeter square, right? You can see smaller square and the larger square. Now each of this large square is now about 0.1 Newton, 0.1, 0.2, 0.3, 0.4, and then so on. In between the large two lines, the large square, then you can see 5 small squares, 5 other lines, right? 4 other lines. So which mean this 0.1 divided into 5 segments internally. So which mean each of this is small square line going to be about like 0.02 Newton value. So that is scale going to change as we proceed the experiment. Okay, this y-axis you have to carefully observe at every given graph because that is scale automatically adjusting. Okay, it may not be the same scale for the small square for the next run and then so on. Now it is easy to measure, right? Let's measure right here. You can see the highest number, highest dot is in between this small square, right? So I can estimate in between small square. This line is 0.5. Each of the small square is 0.02. So this means this line is 0.02. In between that, I can estimate to about 0.51 into 0.01. So that means this dot right here, 0.51. Okay, equation. So this can be simply 0.51 Newton. And the kinetic friction force is actually, you can see that also I may need to get which point I'm going to be measuring, right? You can see number is goes up and down, up and down, up and down here. And in it changes between these two lines. So I'm going to read into the maximum possible number here, okay, very top. So which means that is in between these two small lines. So if you come into the y-axis, this solid dark line 0.2, each small line 0.02, this is going to be 0.22, next one going to be 0.24. In between those two lines, I can read the top of this into 0.23. So those are the little bit of adjustment we have to do looking at the scale here. Okay. So this we're going to read into 0.23. Okay, that's it. It's very simple. After you read them, all I have to do get the ratio, right? So I have to get the ratio equal sign friction force is static over normal force B9 over C9. That will give you the friction coefficient. This is wood on table. We're expecting to be static friction coefficient about 0.5. That's what we got. An equal sign friction force kinetic over normal force. So the kinetic friction always less than the static, and then there's no particular way to tell that how much is less. Sometimes it about 30%, 40%, sometimes just 10%, depending on the surfaces. Okay, so it's about like 40% less maybe. That's very normal. So the function I'm using for static friction coefficient, mu s, represent the static friction coefficient, and then this one is the function we are using for the mu k. Okay, mu k is actually for the kinetic friction coefficient equation. Okay, then let's continue. It's a very simple procedure now. Now you know exactly what to do, right? So what we're going to do, we're going to continue from this data set by increasing mass slowly, and then we'll continue to the next one, and then next one, and then so on. At least 5 data point is good enough to make the graph. Okay, let's increase the mass, rerun the setup. So to do anything, you have to reset the experiment first, and then after you reset, you can increase the mass by clicking these arrows, right? You click that once, it jump into 243. The smallest value, you can go 100 always, okay? Smallest value is 100, I think, but when I click this up arrow, you may not see exact numbers as I observing. That's okay, you write it down what numbers you observing on your side, okay? Because when I click this up arrow once, it jump into 193. But if you click that once from the 100, you may not get to that number. Maybe it will be a different number. That's okay. Write it down what you observe, because the graph, depending on the number what you observing. Okay. So let's click once, 205. That's totally fine. You can start there. Divide by 1000.205 to kilogram, and you can click and drag. That will give you the normal force. And then all we're going to do is that run the experiment, extract the static and the kinetic friction forces, right? Friction. Okay, then it's just let it start and then wait until the object is moving, starting. See that until the graph is actually hit here, object is at rest, right? Let's reset and then rerun again. Observe the graph and the object together, right? See, still at rest, then it broke. That's the idea, right? That's the idea of a static friction force and the kinetic friction force. After it breaks the stability, you don't need such high force to actually move the object. It's going to be slightly less. That's all. Then all we need is to extract these two numbers. Now you can see scale changes, right? Y-axis scale. Now it goes from 0.5, each of these solid dark line. This is 0.5, this is 1.0. Each of this is small line now just 0.1, right? So I can read here maybe in between half of this square, small square, which means that is 1.05, right? 1.05. Following. Any question? That's all. Then let's measure the kinetic. That also we can read to maybe mid of this, right? Not to the very top, not to the bottom here. This is 0.5. This should be then 0.4 line, which mean in between should be 0.45, right? Read to the middle. Oh, I did I it's oh yeah, it's fine. Yeah. Okay, then to do this calculation, friction coefficient, you can just click and drag previous calculated values. It will do the calculation automatically. The observe the numbers, we expecting these numbers to be about the same as we continue because the mass increment doesn't decide anything. As a result of mass increment, your amount of force needed to break the stability also must change because friction coefficient are deciding only by the surfaces which are touching. We are not changing that. Okay, it is still wood cart on the table. That doesn't change. So which means this for static we expecting about to be zero point 0.5. This we expecting about to be 0.2. Okay, still it's good. There will be a little bit of error that's going to be from our reading error because we estimating that midpoint. Question. Okay, and then let's continue. Right, so let's reset the simulator, increase the mass into next value 347. You may not see the exact number which I see. Write it down your numbers, otherwise the force values you getting from the graph will not match. Okay, 0.347, and you can click and drag to get the normal force, and then let it start. Wait until object break the stability. After that happen, all we need is to read this point very top on the static side that we have to read between these two lines, right? 1.5, 2. Each of the small square going to be 0.1. This is going to be 1.6. This is going to be 1.7. This is going to be 1.67. This is going to be 1.8. In between 1.7 and 8, I can read this into 1.75, right? And kinetic, and I think we should read all the way to this line, right? This line right here. This is 1, this should be 0.9, this should be 0.8. We should read into like 0.80. Then you click and drag, that will do the calculation for the static and kinetic friction coefficient. We're expecting those to be about 0.5 and 0.2, right? Oh, it's still fine. There will be little bit of offset. That's very normal because we're doing the estimation to our final decimal place. So because of that, you will see little bit of error. That's totally fine. Question. Okay. So the one other thing now on the table you can see, I have actually both of these into third decimal place, but in terms of accuracy, I can't have that many, right? At any given moment, I can have only 2 decimal places, right? I can't estimate to more than 2 decimal places, right? So because of that, what we should do, we should format that. So at any given moment, for example, right here, I can read into 1.5, 1.6. I can estimate the second decimal place, 1.55, but I cannot estimate the third decimal place. So it's not meaningful reporting 3 decimal places, any of these values. You have to reformat these 2 cells, right click, force static friction and kinetic friction force, format cells, reformat into 2 decimal places. That's the accuracy we can go, right? Okay, question. Okay, good. However, when I go to the static and friction coefficient, I can have three significant places, right? Except this first one, everything else I have actually about three significant figures. Not all, but we'll keep it to three significant figures. They are okay. They will not match exactly perfectly for every single measurement to three sig figs, but let's keep three significant figure there because then our accuracy will be much better. Okay. So please reformat static friction force and the kinetic friction force into 2 decimal place accuracy. Everything else you can keep it as it is. All right, question. Okay, then let's continue. All we have to do is that reset, increase the mass, rerun. Now the mass is 0.421. Click and drag to get the normal force. Then let's start the simulator, wait until the object move. There, then we can get the maximum static force needed to move the object and the kinetic force, right? So that's gonna be in between these two small dot. Right now, let's take a look the scale. This is 2, this is 3. In between should be 2.5. So each of the small line gonna be now 0.1, 2.1, 2, 3, 4, 5, right? So which means this is gonna be in between first and second small line, 2.1 and 2.2. So it should be 2.15 then, right? I can estimate into the second decimal place. That is our estimated point. Question. Okay, then let's take a look the kinetic. Kinetic we should read all the way to maybe, we can't say it exactly in the middle, right? It's very close to the top. Then let's read the top line, I think. That's going to be about 1.0. Check the static friction coefficient and also let's check the kinetic. So we are fine. You can see the error right there, a little bit higher for the kinetic because we estimate to the next line. You can see it become 0.24, but that's okay. Question. That's it then. Reset, increase the mass to next value 0.483. And then click and drag the normal to calculate the normal force. Start the simulator. Wait until it complete. After that, you read the same to point. Maximum point right here is this solid dark line. This is 2. This should be 2.5. 2.5. And then this I should read into the first small square line after this dark line. This is 1. This is 1.5. That this should be 1.1, right? 1.1. So we are about the same, right? These numbers fluctuate a little bit, second, third decimal place, but the first decimal place remaining as it is. Kinetic friction coefficient fluctuates, second and third decimal place, but the first one remaining. So we can basically say that the static is about 0.5 and the kinetic is about like 0.22 or maybe 0.23. Question. Okay, then let's take a look the graphical method. To take a look the graphical method, what we're going to do, we're going to make a graph, right? Now the graph we identified earlier, we have to make a graph, friction force versus force of gravity, right? Of the moving object on the horizontal plane. So let's make that graph here. I have the friction forces, I have the normal forces. To make the graph, you have to insert the graph first. To insert the graph sheet, can do insert. The middle of this, you can see scatter plot. Then always we do is scatter plot first, right? And then we'll add the data, double click on the graph sheet, left hand side, very top, third icon, select data, then add, click on add, then click on the X values, then select the X values. X values should be force of gravity. That's column number C9 to C13. You have to highlight that data set, click and drag, okay? That will highlight automatically with this green color dotted line right here. Okay. And Y values, delete anything there. For static, I need Y values D9 to D13. Click and drag to highlight. Click OK. Click OK again. Then you have the graph. Okay, question. All right, we have a graph. Then the other formatting by now you should know, right? So if I have a graph, double click, then you go left hand side, very corner top, chart elements, then make sure all the axis titles are visible, and then also the trend line is visible. In this case, we need trend line linear, okay? Then if you have a graph, make sure you name it properly. This is the title of what this is normal. This is actually friction force, because when you name in the graph, first term gonna be the y-axis, right? This is friction force versus normal force for wood on table. You have to name it properly because we're going to investigate other surfaces later. Otherwise, graph name not going to be meaningful. Okay, just say friction force normal versus normal force, not enough. You have to specify what. And then x-axis title, normal force, unit Newton, y-axis title, friction force, unit Newton. And if you have a line, then we would like to see the equation, right? Double click on the line, and then right hand side, very top corner, trend line options. Then go all the way to the bottom, click all of these three options. Then you will see the equation for the line. Click and drag that equation somewhere in the middle. We can clearly see R square tells you how good the fitting is. Usually it should be about 1 or very close to 1. Then the fitting is perfect. Now, this we can say, depending on how many figures you're going to have in your procedure, right? So your procedure is going to have about like at least 3 figures. And then also if your theory section have a figures, then the figure number is actually continuous, right? Make sure you're mindful about those things. I'm going to name this as a figure number 3, starting from 3. The reason we're going to have at least 3 different simulator pictures for our procedure section, okay? So if I start from 3, this is going to be now friction force versus normal force for wood on table. Okay, in terms of this formatting, I think most of you doing fine now, except very few. 1 or 2 students still has a lot of issues. They don't rename the graph. Just copy paste this part only. That's not enough. You have to copy paste from here the whole graph to your report. Okay. And also you need the picture of the simulator too. When you take in this picture, it's better to have the graph included with the picture. The reason the graph is part of the simulator, okay? It's not the data, just part of the simulator. I would take the graph, included the picture. That should go into, I will add into here, because the idea of adding all of them into here, when you're preparing the lab report later, you know everything is on your Excel sheet. then it's very simple to proceed. Then you look at everything on the Excel sheet and then do your lab report accordingly. That will make a little bit easier to do all the stuff needed for lab report. Now this is going to be our figure 1. We should go into the procedure section. Okay, and this is going to be the simulator for friction. Right, so 2 other simulators we're using later, we will add all those pictures here. Okay, then going to be 3 figures there. Because of that, I'm starting here naming the graph from figure 3. Okay, all right, so any question? Okay, then let's continue. There is a problem with my Excel sheet. I think you see that all the data looks disappear all of a sudden. So sometime if I have many application opens, this computer becomes very slow. It happens sometime. Let's see. Hopefully it will be okay. Let's do the average here. Calculated average, friction coefficient, equal sign, average command, average, and then I have to average out all the static friction coefficient, which is on cell number F9 to F13. Data is there, but my Excel becomes very slow responsive. I think on your side you should be fine. Okay, 0.521. Average command, the mu cal avg. For static, I'm going to use static inside the parentheses. Show this is for static. Okay, do the kinetic average is the same, equal average command, and then cell values G9 to G13, and that will give you this kinetic average. So it's going to be then mu cal avg, but for kinetic. Okay, question. Okay, as we now we are on almost like half the semester done. Okay, after next exam, after exam number 2, the way we do experiment will be completely changes. Will be completely changing. So we're gonna go back to like breakout rooms, and then you guys has to work together, and then I'm gonna investigating every single student, whether you are participating or not. There are changes coming in. If you're not ready for that, then you have to get ready yourself. Okay. So if you're just observing this or keep it record and then do the lab later, that kind of things will no longer work after next week. You will get 0 point. And those are the things I will send you a detailed email. Okay. After next exam number 2. All right, because by now you should have a really good idea what type of data table we're creating, what type of report we're creating, how the report is done, how the data table done with the Excel. I don't think I have to go through every single calculation this way. Throughout the next few experiments, we have only few experiment remains. Those becomes much easier actually even than this. Because of that, we're going to go back and then try to do like the group work. 13, but there's no group report still. Okay, everybody individually will report, but you're going to participate and then do as a group, like maybe 2-member or 2-member group in the breakout rooms with the WebEx still. Okay, those things we'll discuss maybe after next week. Okay, so let's continue from the graph. You know, you can calculate the friction coefficient. That's going to be simply slope of the graph, right? 0.522, 0.522. And then I can do the percentage error between calculated average and the expected value from the graph equal sign. ABS parentheses, calculated average minus graphical value, divide by calculated value, multiply by 100, that's PE. But I would like to do, let me tell you that too. We would like to do percentage error, but there are two types of percentage error. We discussed this sometime. Percentage error PE, usually we do if I have a standard value, right? Like the gravitational constant or known value like the density, things like that. Then there's another percentage error. We do percentage difference if you want to compare two experimental values, right? If you want to do that, we usually do PD, not PE. Change this term into PD, and then let's do percentage difference for this case. No meaning doing percentage error because there's no standard value at this point for these numbers. Okay, equal sign, ABS, calculated average, ABS parentheses, calculated average minus value from the graph, difference, divide by only difference between PD and PE. Denominator is actually the average for this case. That's the only difference. Okay, double brackets, calculated average plus value from the graph, divide by 2, close brackets, multiplied by 100. Very, very small percentage difference. That is the command for PD. Right, so then I need to just investigate the friction coefficient kinetic by using the graphical value. To do that, I need to make another graph. So we're going to do this another few more times, then it's going to be too many graphs. Because of that, what we're going to do, we're going to include that, add that data set into the same graph. The reason, at least one parameter, one axis is going to be the same. In this case, the normal force going to be common axis. As far as you have one axis same, you can add the data into the same graph, right? Let's add the data into this same graph. Double click on the graph. Right hand side, very top, select data. Click add. Then I can add the new data set. You can actually name this series. This is actually kinetic. Previous series also we can rename, that is static. Okay. And series X values is the normal force, C9 to C13. Series Y values, friction force kinetic, E9 to E13. Click OK, and then go to series 1. Click edit, and then type the name there. This is static. Then we can identify which color is which, okay? Because now there's two different data set on the same graph. I need to know which color is which. You can do that easily by putting the legend. To put the legend, what you have to do, double click on the graph, left hand side, very top chart element. You can click legend here and put the legend somewhere maybe on the top. So that will automatically appear there. Now you can see blue color is static, orange color kinetic. Okay. Likewise, you can add many data point, many data set. At least one axis should be common. Otherwise, it's no meaning putting everything into the same graph. You can see top of the graph is actually the friction coefficient. So the orange one, kinetic, has a smaller slope. So which means it has a smaller friction coefficient. Friction. All right, then let's add the trend line. To add the trend line, you can just go into the chart element, trend line, click on the add trend line linear. Then it will add the trend line, new trend line to the new data set. And I need to see the equation, double click on that new trend line. And then go all the way to the right hand side, very bottom, then click all of these three options. That will give you the new values. Okay, that's the equation and the numbers we would like to see for our kinetic case. Friction. That's all. Then let's continue. Graph value from the kinetic value from the graph 0.235. And to do the percentage different, you can just click and drag, right? That will do automatically for you. So very small numbers, percentage different values, because our numbers are almost close to perfect because we're doing everything with the simulator, right? Okay, any question? All right, now next two graphs, next to part of the experiment, table number 3, 4, and then 5, 6 is exactly the same as the previous. There's no difference at all. But let's continue. But that is why actually after next exam, we're going to go back to a different kind of setting for the experiment. Then we will discuss like this part we done here in detail, and the next two part I will ask you to do in terms of group of settings. Then I can see actually in detail who's doing what. Okay, so that will be easier for you guys too, because then you can actually do yourself and then learn how to do this during the class time instead of maybe waiting to see the video or something later. Okay, so there's no difference. Table number 3, only difference we're going to do, we're going to reset the simulator and then change the type of the surfaces into maybe rubber or ice. To do that, all you have to do, click on the word wood right here on the left hand side top. You click that, it will change into rubber or ice. Exactly same process. There's no difference at all. Just repeating the experiment 2 more times for 2 different type of surfaces. Okay. Question. Okay, then let's continue. Click start, and then we'll start again the lowest possible mass values we done earlier, right? So maybe like 100. And then all you have to do is the same thing. Click on the start button and then wait until the simulator done. Then I need to extract these two numbers. Right now you can see the rubber on ice. Now these are actually very smooth surfaces, right? Because of that smoothness, now you can see the force needed to move the break the stability is actually very small. Now it's no longer large at all. It's 0.1, and then after that changes a bit, but not changes that much like for the wood on the table. Okay, completely different behavior. So let's read this now. Each of the dark solid line 0.1, and the next one is 0.15, next one is 0.2, right? So which means each of these inside lines should be about 0.01. I can estimate another number in between, right? So which means this is 0.1, then this line gonna be 0.01, 0.11, and then I can estimate in between if I want to. Okay. All right, so let's see what number I need. This line right here, and the second small square, 1.11, 0.12. Static friction maximum 0.12, and the mass 0.100, force equal sign 0.100 multiplied by 9.81, and the kinetic force needed 2 small squares lower than this line, so that is 0.1. This should be 0.08. This should 0.08. This line right here. 0.051, right? Should be then 0.08. You can see difference is not big like the previous. Okay. We can keep the third decimal place here because I can actually estimate to that third decimal place right now because the numbers are very small. Okay. Which mean about 3 significant figures like we done earlier. And the same thing, ratio between the normal friction force, static versus normal force, and then ratio between the friction force, kinetic versus normal force. You can see the numbers are very small, extremely small, because the friction is extremely less between these two surfaces. Okay. Mass is measured in kilograms, normal force measured in unit Newton, friction force measured in unit Newton, friction force kinetic also measured in unit Newton. Okay, equation. Okay, then let's continue. All we have to do is that increase the object mass and then see how the friction forces are changing, right? So click the up arrow once, and the commands are exactly the same like you done earlier, right? There's no difference at all. Let me copy paste that anyway. For every table, you have to collect the commands. Normal force and the friction coefficient. Mu static and then mu kinetic. Okay, equation. Right, next mass 0.206. Run the simulator and then extract the numbers. So I can read the very top right here. There's a dot right, just one small square below this line. This is 0.2, this is 0.3, this should be 0.25, this should be 0.24. 0.24. And then kinetic I can read into one small square above this solid line, dark line. 0.1, 0.15, next small one, 0.16, 0.16. And then normal force, you can just click and drag, that will do the calculation. Friction coefficient, you can click and drag, that will do the calculation automatically. And see, number should be about like 0.12 here. So I'm still getting the same, about 0.12 if I rounded into 2 decimal places. About 0.8, about 0.8, we are good. That's the one you have to check, because if those numbers are very largely deviating, then we may be doing something wrong either in the calculation or in the reading right here. We have to go back and recheck. Okay. And that's all. Then you reset and then click up arrow once, 0.376. And in the normal force, it's the same, right? Just click and drag, and then all we have to do is start button. Wait until it runs, then we'll read the values. Okay, any question? Okay, then let's read the numbers. Very top I can read into second small square after 0.4. That should be then this is 0.4. Now the scale changes, right? Now this is 0.4, this is 0.6, this should be now 0.5. So each of the small lines should be about like 0.02, not 0.01. So this is going to be 0.42, 0.44. Should be 0.44. And this we can read all the way to this solid line. So that's about 0.3. Then let's check the values for the static and kinetic coefficient. That should be about the same like the previous. Then we are fine in terms of calculation. Okay. Any question? Okay. Then let's continue. Let's increase the reset. Increase the mass one more time. 0.483. And start. Wait until the simulator completed. Then we'll extract the numbers. Normal force, you can just click and drag. It will do the calculation automatically. Friction force is static. Be all the way to two small squares below 0.6. So that should be then 0.58, right? 0.58. And static and the kinetic I can read into one square below 0.4. So that should be 0.38 then, right? Previous number should be 0.56 actually, not 58, because two squares below, right? This should be 0.5, 52, 54, 56. And new number should be about 0.38 because that is one square below 0.4. 0.38. Let's check the static and kinetic coefficient. You can just click and drag and then check the values. Okay. Static should remain about the same. Kinetic should remain about the same. Those numbers should not change as a function of mass. Those numbers change only if you change the surfaces. That's all. Then you reset up arrow once, redo it. One square below about 0.8. This is 0.6. This is 0.7. 0.72, 74, 76. I should read maybe in between these two, 0.77. And then kinetic to maybe we can read directly to this number 0.5. And mass is now 0.653. And we are really close to the numbers we expected. Friction. Okay, then let's do the graph. Now you know we done the graph earlier. We just gonna do the same thing. Because of that, since it is the same graph, what I'm gonna do, I'm gonna make a copy of this graph and then use that. Okay. So you only have to do click on the graph, copy, and then paste into here. You can actually make new, doesn't matter. But I'm gonna copy that graph and then edit the data set, because everything else remain in the same. I don't need to write the graph topic or the axis labels or anything. Okay. So all I have to do just edit the data set. That's all. And I can copy paste figure name also. This should gonna be figure 4. All I have to change there is actually what the object and the surface. Now this is rubber on ice. Rubber on ice. And let's edit the data. Double click, right hand side, top number 3 icon, select data. Then you can see it actually highlighting the previous table because it's reading is still the previous data. You have to edit it. Click on this static, edit. Then you can see X values right here reading from the previous table. You have to delete that and then go to table number 3. Highlight the normal force, that is C26 to C30. That's the new static. Okay. Then delete everything on Y and then go to table 3. Highlight again static friction force D26 to D30. Click OK. Click OK again. Then it will readjust everything, but you can see it little bit becomes mess there because now static goes below the kinetic. The reason is still this kinetic right here reading the previous data. Okay. You have, after you edit all the data, it will look fine. Let's edit the kinetic. Double click, select data, click on the kinetic, edit, delete everything on X, go to table 3, C26 to C30. Y values, delete everything there, go to table 3, E26 to E30. Then click OK, click OK again. Now you can see it's everything becomes normal again. Kinetic always must be lower than the static. Okay. That's true for any sort of friction experiment or any sort of friction happening anywhere in two surfaces. Okay. That basics cannot differ at all. Now we are fine. We have all the information there, and I have to edit the term here. We also should be rubber on ice. Okay. Question. Okay, then let's continue. So continuing to table number 4. Again, we're going to do the same analysis we done for the previous case. Calculated average from the table 3 equals sign average command, and then the static go from F26 to F30, and static from the graph, the number in front of the X, slope of the graph 0.1195, 0.1195. So it read into exactly the same, right? You see that? That because it's rounding into three significant figures, right? So the best way is that actually, since it is a graphical value, I can actually keep one more decimal place there. It's inside there, you can see. It's already there, but it's look like it's not there. The reason we are actually asking cell to show only 3 decimal places. That's why. Okay, but still we can do the percentage error. Equal sign. We do in percentage difference. Okay, please edit that. There's no meaning doing PE. Instead, we'll do PD because we're comparing two values we extracted from the experiment. Okay, PD equal sign ABS parentheses, calculated average minus graphical value, divide by double brackets, calculated value plus graphical value, 337 close bracket divide by 2, close brackets again multiplied by 100. Average command U L E in the PD command. And let's do same calculation for kinetic question. Okay, same calculation actually equal sign average function, and the kinetic is cell F26 to G26 to G30 equal average G26 to G30, close brackets, hit enter, 0.8080. Let's look at the graph. Orange color line is actually for the kinetic. It's about 0.0793. 0.0793. 0.0793. Okay. Let's do the PD. You can click and drag for that one. Average command for the new cal kinetic. Okay, question. Right, then let's continue. Next one is that we're going to do the same, but for completely different type of surfaces. So let's try maybe metal on metal. That would be very different than what we're observing so far. Wood on wood we try 0.5 static, and then rubber on ice about 0.1 static friction coefficient. Let's try metal on metal, reset. Click on the word rubber, then it will change into aluminium on its tail. So let's go back to the smallest mass. It even doesn't matter really, you can start any mass, doesn't matter, but make sure you report accordingly, okay? So I'm going to start everywhere, every step here with the lowest mass. Okay? And it's the same, exactly same experiment. There's no difference at all. Mass in kilogram and the normal force in unit Newton, static force unit Newton, kinetic force unit Newton, and the coefficients are unitless. All we have to do just observe the simulator graph with respect to the mass of the object. That's all really. Okay, any question? Okay, so if you don't have any question, I think we'll take a quick break here, and then we'll start in about 10 minutes, okay? And I think we can finish a little bit earlier today the experiment, then we can take a look one or two questions from the last chapter, okay? All right, then let's continue. Now we done twice the same kind of calculation. It's we're going to do one more time that calculation and analysis. Then after that, we're going to change the way we're doing the experiment into a different type of the setup that will more align with the setup if we do in the in-class setting. The next simulator will more align with that setting. Okay, so that will give you better idea like how we're going to perform the experiment in class setting. And then at the end, we're going to take a look at the inclined version that also we can do in in-person setting. Okay. So let's take a look at least one trial for completely different type of surfaces. Let's do metal on metal, right? So I start from the 100, click start. Please ask any question, okay? Metal on metal, 0.100 is starting mass. Normal force is going to be equal mass times 9.81. And friction force is static. I can read into this is small square, right? So the value of that would be, this is 0.6, this one is 0.7, each small square going to be 0.02. This should be then 0.62, right? Yep. And I can estimate one number because I can estimate in between small squares. Okay, we can keep the decimal place. And the kinetic can read all the way into this line, right? One square below the solid dark line here. That should be 0.5. One number below should be 0.48. 0.48. Static coefficient equal static friction force divided by the normal. Kinetic friction coefficient equal kinetic friction force divided by the normal. Divided by the normal. Okay, so we're getting about like 0.632 metal on metal, slightly above wood on table, and then we're getting about 0.489 for the kinetic. Now you can see those two are not decreases like in for the wood case, right? So close by both of them. And then let's continue this by increasing the mass of the object. Reset, increase the mass, start again. And after object start moving, we can read these two numbers. Now this is 0.5, this is 1. So I can't read into midpoint right here, right? It's too low. So I should gonna just read into 1. So mass of the object is 0.168. Weight you can click and drag. And the static is I'm gonna read into just 1.0. Kinetic. Kinetic we can read into this small square line that is too lower, 1.0, that should be 0.5, 0.6, 0.7, it should be 0.8. And the coefficients you can click and drag. About same, so we are good. So that's the one you need to check always. Okay, if those numbers are very different, then we might doing something wrong when you read in the numbers. Okay. And that's all. Then you just continue, just reset it, increase the mass, run it again. Mass is 0.25. Weight you can click and drag. Static, I can read maybe into half right here, right? Midway. So which means this is 1.5. This should be 1.6. I can read that into 1.55. And the kinetic 2 squares above this solid line 1, this should be 1.1, this should be 1.2. 1.2, and then let's check the coefficients. We are good. So that's the one you have to check, okay, whether you are close by or whether there's anything huge difference. Static always should remaining about 0.6. Kinetic in this case look like remaining about 0.48. Okay. And let's increase the mass and then rerun, reset, increase the mass, rerun the setup. Mass is 0.403. And the maximum point is, this is 2, this is 3, this should be 2.5 then. 2.5. I can read halfway here. That means I should read into half in between these two. This is 1, 1.5, 1.9. This is 2. I can read into 1.95. Weight you can click and drag. Coefficients also you can click and drag. So we good. So the numbers remaining very consistent. Reset, up arrow once, start. Mass is 0.562. Static max is this line right here. That is about 3.5, right? 3.5 exactly. And the kinetic gonna be 2 squares above this solid line. This is 2, 2.5, 2.6. It should be 2.7. 2.7. So we good. So these numbers remaining consistent. These numbers also remaining very consistent. Question? In terms of function, those are the same kind of function, all three tables. Okay. So the normal force, friction coefficient, mu stat, and mu kinetic. Okay, guys, any question? Okay, let's make a graph then. It's the same graph. I'm gonna make a copy of the graph number 2. Copy and then let's paste into here. And then you can also copy the graph name. It should be now figure number 5. Only difference is now this is aluminium on steel, right? Aluminium on steel, right? Name it properly. Let's take a look at that again. I think yeah, aluminium on steel. Good. And the figure name also you have to rename, right? The steel, and then everything else remaining same. Okay, nothing changes. And all I have to do now, insert the new data because this is still reading the previous table. Okay, rubber nice. Let's double click. Right hand side, very top, select data, static, edit, and then delete everything on X. Go to table number 5. Table number 5, normal force should be C44 to 48. And then Y values should be for static friction force, D44 to D48. Click OK. Click OK again. So we have a line, that's blue line is for static new. But you can see two lines are very further away. The reason is still that the kinetic read in the previous data, you have to edit that. Double click, right hand side, very top, select data, kinetic, edit, delete everything on X, and then go to table 5, C44 to C48, delete everything on Y, go to table 5, E44 to E48. Click OK, click OK again. Those two graphs should be close by each other because you can see the friction coefficient are much closer. So the slope of the graph should be much closer to each other, right? That's what we're observing. Make sure you click and drag this equation. Those should be visible very clearly, should not be on the graph or anywhere which crossing any other things. Question. Okay, then let's continue. Table number 6, calculated average. Again, the same thing, equal AV. Average value is static. Cell F44 to 48. Close brackets, hit enter. That's the cal average for static. Okay, so do that from the graph, you know the number in front of the x now, right? It's very simple, 0.632. These two numbers should be close by. Yeah, we are very close to each other. Percentage difference we're doing. Make sure you edit that term to PD equal sign ABS parentheses, cal average minus graph value divide by double brackets, cal average plus graph value D54 divide by 2 close brackets multiply by 100. That's the equation for PD. Friction. Do the average for kinetic then. Average for kinetic cell G44 to G48. Be then mu cal Vg, but for kinetic. Okay, then from the graph, number in front of the x, 0.4905. Very close. You can click and drag the PD, then that will do the percentage difference. All right, question. So by now you should have 3 different graphs. Each graph should have to have 2 lines, okay? And you have to have a 1 simulator picture. And we completed about 6 tables. Let's go to table number 7. Table number 7. Now, if you go into this, anybody have any question? That should be very easy. It's the same calculation we're doing actually again and again. Even for say table number 7, only difference come table 8, 9, and 10. So table number 7, it's the same kind of calculation, but the difference is that if in the simulator you can see it actually has other type of surfaces. If you take a look carefully right here, after aluminium on steel, if you click on there again, it will go into glass on glass and then 2 other different options. So let's take a look at least one calculation for each, because there's no meaning doing this detailed analysis. You can see it's almost the same kind of calculation, only the surface difference. So let's do at least one calculation, only one time, per each object and surface, okay? Next, object and surface, glass on glass, glass on glass. We need the mass of the object in unit kilogram, normal force, unit Newton, friction force is static, unit Newton, friction force kinetic, Newton, and then we can calculate the static and kinetic coefficient, but we're going to do only once per each object. Okay. All you have to do, you can keep the same object mass. No meaning changing, just let it be there like that. 0.562 plus 562 grams divided by 1000 equal sign mass multiplied by 9.81. You will get the normal force. We're doing only one calculation. This is a normal force function. And its rest is same. Technically, just run it and then wait until the object start moving. Then we know we have the maximum friction force and the kinetic, right? Then let's extract that data. This point right here, middle of these two lines, this is 4.0, this should be 5.0, this should be 5.2. I can measure in between, which means 5.1, right? 5.1. But now you can see I can't go 3 decimal places. That is wrong because I can go only estimated value in between, right? So I can go 5.2, 5.4, 5.6, 5.86. So which means all even values I can estimate. That's all really. I can't do any other estimation. So I can go either 4.0, 5.0, or in between each even values 4.2, 4.4, 4.6, 8, and 5. I can estimate in between. All are again down to first decimal place, not more than that. Okay. So which means these two, because the numbers are much larger now. That's why earlier I mentioned many times today, this is scale Y scale is changing for every single measurement. Okay. Right here, only these two cells are gonna reformat into only one decimal place. There's no meaning keeping more than one. Okay, kinetic gonna be, I can read into midpoint in between these two small squares. So which mean, let's say this is 2, 2.2, 2.4. I can go in between 2.3. And the ratio, static over normal. And the ratio, kinetic over normal. Now you can see this is glass on glass actually have a highest, so far we measured it's 0.925, because glass on glass, to break the stability, it actually has a huge attractive force between glass surfaces. Because of that, you have to have a really large force to break the stability, right? So because of that, the friction coefficient is actually much larger. Is mu s. Yes, and then mu k. Right, question. Okay, let's check a couple of other surfaces to see how this is affecting with the surface. If you reset and then click on the glass, it will change into graphite on graphite. Let's take a look. Graphite on graphite. Mass, we're going to keep the same. It's not much meaningful measuring or changing that because we're not interested how to observe that or making the graph at all. We just need to see only one number. Keep the same mass, click start, and then wait until the program run. Now you can see the kinetic max and the static max and the kinetic is extremely close for graphite. This is, I should read, can't read into midpoint actually. I'm going to read into just 1.0 there. This is 1.0, this is 1.1. I can go in between actually if I want to. So which means I can have 2 decimal place for this calculation. Okay, can't have 3, I can have only 2. So I'm going to reformat that into that. So the previous numbers, since I can measure static and kinetic into only 2 significant figures, I should have here in these values 2 figures. Now you can see even the same table. Depending on the experiment and then how you report the data, you have to readjust the data. You can't just format the whole data as a single formatting. Okay, you have to separate out cell by cell. You should be able to reformat according to the observation and the calculation. Okay. On the other hand, kinetic is I should be able to read maybe to the midpoint right here. Even not midpoint, I should not read into midpoint. Slightly lower, and then these two are extremely close by. Let's read into this line. That should be about 0.9. Otherwise, these two values extremely close. Check the friction coefficient, 0.18 and then 0.16. Actually, those are the smallest probably we got. Let's check earlier, we got 0.12 and then 0.08 for rubber on ice. That's the smallest. This is after that actually. Very close to the rubber on ice, that much. Less friction on graphite on graphite. That's why the graphite particles and then the graphite dust used as a friction to reduce the friction in certain applications. Okay, question. Let's do one trial and then start the next section. Okay, reset. Click on graphite, then let's check rubber on concrete. Okay, start. Mass I'm gonna keep the same. Weight will be remaining the same. Force is much higher now, so which means the friction will be higher, of course. This is 4.0, this is 5.0. I can read only to 1 decimal place. It will be 5.2, 5.4 maximum. 5.4 we can read into only 1 decimal place. And the kinetic I'm going to read into this solid line 4.0. And then let's check the coefficients. About 0.98 and then 0.73. So those are the highest actually. So far we measuring. So the rubber on concrete. Okay, question. All right, then let's take a look the different type of setup. We can do the same measurements, but the setup is completely different. They click on this link right here for part B. Page number 3, part B. Then you will get it into a new page. Should be look like this right here. That's a completely different setup now. Okay. So that our table number 8, static friction with the hanger mass. This setup right here, we can actually do only simulate only for the static. But if we're doing this in class, this is exact setup actually we will be using. So the setup is very simple. So the how it set it up. This is our lab table. We're going to have a pulley attached to the end of the lab. Then there's the cart, wooden cart, and then it has a attachment with the string, other end of the string connected to the hanger. And then hanger weight usually about like 50 grams in the beginning of the experiment. And then if it is in class setting, we actually have we actually can change the mass slowly, like maybe 10 gram, 5 gram, even 1 gram. But the simulator change like maybe I think 100 gram at a time. That's okay because I think internally they set it up everything. We can't do any changes there. But the numbers we will be getting about right. Okay, they set it up that way. But technically, if it is in-person setting, this mass on the hanger can change very small values. So what we're going to do, initially the setup is stable now, right? Cart is not moving because there's no enough mass on the hanger. All you have to do, add the mass into the hanger, and at some point you will see stability break. Object will be starting to move to the rightward direction. Exactly that moment, we want to find the how much force is on the hanger. We can find the how much total mass in the hanger multiplied by gravity. We can find the what's the tension force. Same tension force applied here to break the stability. Static force going to be equal to that tension force. That's the idea. Okay, question? Okay, then let's take a look. This is now our simulator. You can see on the left hand side we can still do different surfaces, but no meaning, we already tested all of them, so we will do only wood on wood. Okay, so we will be doing this only wood on wood. You can add that information to the very top of the table topic. We will be doing wood on wood only. Okay, and mass of the hanger I need in kilogram. Force of gravity, unit should be Newton. Maximum static force, I can find the unit of Newton, and the static friction coefficient is unitless. Okay, let's start. Left hand side, there's a small area where we can change, adjust the values, right? So in that menu area, block weight is starting with the 1000. That's the smallest we can go. Let's start there. Block weight represent what is the total weight of this object on the table when it is starting. 1000 grams means 1 kilogram, and the normal force is going to be equal mass multiplied by the gravity. All we have to do, let it increase the mass on the hanger. When the object move, I can find the static force directly. Okay, to do that, what you have to do, there's a slider right here. You can see a slider right here, says the hanger weight is starting at 300. You can click and drag, but instead of dragging, I would do click on that slider, this blue dot, then use the arrows on your keyboard. Then it will increase like according to the preset values. Okay. If you click the arrows, it will slowly increase. Now you can see I'm on 400. You can see the graph also, which we observed earlier, is still now in motion. Immediately when I go to 500, it's starting to move. Maybe the real value in between 4 and 500, because simulator doesn't allow us to change smaller values. That's why if you're doing this in class, we're going to have to change those mass very slowly, maybe 10 gram, 20 gram at a time, to identify the location of breaking stability point. Now in this case, I can't do anything. Force of static equal total mass on the hanger 500 grams, so which means divide by 1000, 5.5 gram multiplied by 9.81. So that will give you the static force maximum needed to break the stability. When you know ratio between the friction force and the normal force is actually our calculated value. So let me write it down, these few commands here. I'm using one command here. This is to get the normal force. Okay, and then this one to get the friction force. Friction force. All right. So this one to get the friction force. This actually now you know how to do all of this without any problem. Okay, and then the ratio to get the friction coefficient. Okay. Okay, so any question? All right, then let's continue this also by changing the weight of the wood block to see. That's what exactly we will be doing if it is in present setting, right? So let's continue. Reset the simulator. Let increase the block weight. I need about like 5 data point. I have freedom of increasing 1000 to 3000. If I go each 500, that should be fine, right? So let's go each 500, 1500, which means 1.5 kilograms. Of course, I can get very easily. Click and drag, and then click on the slider for the hanger weight. Click the arrows until object is starting to move. After it move, I just need total mass on the hanger 800. So which means 0.8 multiplied by 9.81, and then click and drag. That will give you calculated static friction coefficient. We expecting this is wood on wood about 0.5, right? That's what we see, but you can see the error is a little bit higher here. The reason I think that exact point where the motion happened, maybe not between 200 values. Maybe I have to go very smaller increment, so that part is not allowed in the simulator. So that's why the error we see there that much. Otherwise, in this case, there's no any observational error. So the error is already attached to the simulator itself. Okay. Then reset, increase the weight of the block to maybe next round value 2000 kilogram. That means 0.2 grams. And then click on the slider for the hanger weight. Increase the hanger weight slowly. At some point, object start the motion. Then we know static friction force is equal total weight on the hanger now 1 kilogram, 1000 grams, multiplied by 9.81. It's going to be 9.81 newtons. Take the ratio about 0.5 and reset. Increase the block weight to 2500. 2500. Click on the hanger weight. Increase slowly. At some point, stability breaks. Object moves. Then at that point, we know now we have 2.5 kilogram. For the block weight, equal sign total weight of the hanger 1.3 kilogram multiplied by 9.81. Ratio between those two about 0.5. So it's remaining consistent about 0.5. Take one data point, reset. Let's increase this all the way to 3000. So which means 3 kilograms. Click on the hanger weight, slowly increase. Okay, after it break the stability, then we can extract and calculate the friction force static. 1.5 gram totally, 1.5 kilogram totally on the hanger times 9.81. And the ratio should give us about 0.5. All consistent. Question. Okay, then let's make the graph like we done earlier, but I need only one graph, but I will copy paste this graph because everything is there. So the editing gonna be easy. And also the graph name I can copy paste from the previous. Okay, and then now this is going to be figure number 6, right? Figure number 6, 3, 4, 5, 6. Figure number 6. Now this is same friction force versus normal force, but for we can say with hanger mass, then I can identify this is a different case, right? Hanger mass, and also you can edit the data now like we done earlier. Double click on the graph sheet, select data, and the kinetic part you have to completely delete, remove the kinetic, click on the kinetic and then remove. There's no kinetic version for this. Static, click on that, click on the edit. Now that I have to select the data, delete everything on the X, and then I have to go data table number 8, normal force on D68 to D72. Delete everything on Y, data table number 8, normal force C68 to C72. And then click OK, click OK again. You should see that nice graph. I do something wrong. Because the slope is 1.9, that's very unlikely. So let me take a look whether I did something wrong. I know axes are flipped. So let me go here, select data again. Make sure axis is correct, static, edit. X value should be normal, right? I think I mixed up the two axes. Normal is C68 to C72. Y values should be static friction force. D68 to D72. Click OK, click OK again. Now, if you look at the slope of the graph, that should be about 0.5. Okay, that's how you can identify whether you've done a mistake or not. You have to be vigilant, and then you have to have a good idea about what kind of result we expecting. In this case, we have a very good idea about the result, what we expecting, right? So accordingly, you need to take a look. What's the information given after the data analysis? Then you have to think whether it's correct or not. Okay, question. Figure number 6, our fourth graph. Let's do the table number 9, percentage error analysis for this case. Equal sign, cal average, AV, average function, and then I have to do E68 to E72, 0.511. Cal AVG, and then from the graph number in front of the X, the slope of the graph 0.5089, 0.5089. Close by, but there's a little bit of error. Let's do the percentage different, okay, not the PE, instead PD. Equal sign, ABS parentheses, cal average minus value from the graph, divide by double brackets, cal average plus value from the graph, D79, close bracket, divide by 2, multiplied by 100. Question. All right, then one last thing we have to do here, check actually the inclined version, right? Earlier, remember I mentioned the inclined version we can use to measure kinetic coefficients. Let's take a look. This inclined version actually may be more
Professor,
interesting. Yeah.
do we need a picture for the simulator?
Yes, we need the picture for the simulator too. Correct. Let's take a screenshot for this one, and then I will add that also into here just to make sure we get that. So that will be right here. Let's do, that will be actually figure number 2. Okay, so that will be your figure number 2 should go to the procedure section. Okay, and let's copy this into here. It's going to be simulator for friction with you can say hanger mass, and then this one you can say more details, for example with force sensor. Okay, so that's I mean, depending on the situation, you may have to give a little bit of extra information uh, to the figure names. Okay, right, so let's see the last one. So the last one is actually inclined plane. This is more interesting because we doing a lot of correction earlier, last 2 chapters for the inclined plane, right? Let's say I have let me draw this exactly the same direction as a simulator. Let's say I have a plane right here, and then that's the ground. Okay, and then let's place the object and then slowly bring this up, slowly increase this direction, but this side right here we keep it fixed, this point. Okay, if you're doing this in person setting, this is exactly we're going to do. So this apparatus is going to be fixed this point, and then one person can actually hold here and then increase. Other person has to have a protractor here somewhere exactly at this location, a protractor. Some of these apparatus have a inbuilt protractor. It actually has a protractor here. You just need to observe. And then at some point, what will happen when this inclined plane is, let's say, somewhere here, then at certain point, object will starting to move. You have to read the angle exactly when the object is start motion. Okay, let's say this is the place where the motion is start. Where the motion is start, right? If that is the case, let's draw a free body diagram for there, right? I have object here, and then your free body diagram gonna be, now you guys are expert on this, right? Free body diagram, things like that. And I have a normal axis here, normal force. And then now object is moving on the plane. Because of that, we can keep our x-axis up and the y-axis here. And now I need this force component of mg, right? This is theta. This one is 90 minus theta. As a result, this one will be theta. If you take the components towards the where the angle is measured, that's going to be always cosine theta. If you measure the component away from where the angle is measured, away from that, then it's going to be always mg sine theta. Now let's take a look at the free body diagram and the motion exactly when the object is breaking this way. At that exact moment, right? If I consider exactly that moment, object is still at rest. So if I consider that and then analyze this free body diagram, then you will get, if I do, if is force is equal mass times acceleration on x direction, then you will get simply just mg cosine, mg sine theta, right? And then that is actually negative direction. And then what is against that is actually the friction, right? Always, if object can sustain there, that means there should be a friction force. positive direction you have friction equals 0. There's no motion, okay? Just before the motion start, which means this is static state. So now you know static force is equal just mg sine theta. If you look at the y-axis on the other hand, there's no motion at all. Normal force minus mg cosine theta equals 0. Normal force is equal mg cosine theta. Now you know what to do, right? So you take the ratio because you know mu s is equal friction force over normal force, right? You take the ratio, you will get mg sine theta over mg cosine theta. Mg cancels out. You will get at the end the static friction coefficient is the tan of the angle of the inclined plane. So that's very interesting because this is independent of mass. So which means the similar case earlier, right? Earlier you have seen the friction is actually independent of mass. It's not depending on the mass, how it decided by actually the surfaces, right? So this is exactly the same. So we can investigate that. We just need the inclined plane apparatus and then little bit of different masses, and then we can check whether it's independent of mass or if it is depending with the mass, and then so on. There's a way actually we can do this for static and kinetic both, but the simulator doesn't allow to do that. For the simulator, we can do only static version. Okay. Question. So this free body diagram, this kind of small equation analysis, those are useful for our lecture class too. Okay, that's the important part actually there. Now for that simulator, you can click on the third link on the part. This should be part B. That's my mistake. It should be a typo. So page number 3 has another simulator. Should be look like this. Click on the begin button, and then you will see a simulator look like this. And then that has an object yellow color, and then you can see right hand side very top there are different options. I can change the static friction. Let's change this into something close to 0.5 because that's going to be look like then wood on wood, right? Let's click this up arrow, change that into maybe close to 0.5. That would be a better number to check because if it is in-person setting, we will be doing wood on. Okay. And kinetic, we can't check anyway, it's slightly less. And the block mass, we can start maybe the lowest possible in this case, 536 gram, we'll start there. Gravity, keep it as it is. Object mass, kilogram. Theta gonna be angle, gonna be unit degrees. You can find the degree symbol, insert symbols, then you can find the degree there, okay. And the coefficient friction, the friction coefficient is actually a unitless parameter. I can compare that number with the number on our simulator. Okay. So let's check with the initial mass 0.536. We're expecting that that not has no effect because that should be the case because we know mu is just tan theta, right? So let's check that. So all we need to do, we need to increase this, we need to make this inclined version. So if you click on right here, it says click to change the angle. If you click that, you can see angle changes, right? See that you can freeze whenever you want to. What you have to do, you have to observe carefully whenever this system shows object is starting to move or breaking the stability. At that point, you have to freeze because we need the angle exactly that moment. Any error there, our observation error, now you can see I have to observe the motion, click the freeze, then the human reaction error there. Because of that, you will see after calculation, maybe we will not get exactly 0.55. We will get close by, may not be exactly 0.55 because the human reaction error always there for this part. Okay, let's do that. Change, click on change angle, keep the cursor on top of the freeze, observe. Whenever the motion is start, freeze it. Right there. So you can see there's a little bit of reaction error. Okay, when I click that, it already start the motion, but I have to click whenever it's starting the motion. Okay, so let's read that angle. Angle is about 29.8. Mu we know just I can't go this many sig fig, right? I can go only one decimal place. Please reformat that column into one decimal place. Column C on table number 10. Friction is just the angle of that, right? Equal sign, tan, parentheses. You know Excel has this, the preset, everything should be in radian. I have to have radian commands there. Radian command first, and then the angle, cell number C85, double brackets cos, hit enter. So we're getting about 0.573, expected 0.55. We are very close, but not exact. One reason, one error is the human error, but the observational error attached to that, the reaction error. Equal sign, this we can do PE because we're comparing with the given value. Okay. Equal sign ABS, parentheses, given value 0.55 minus calculated value, divide by 0.55, given value multiplied by 100. So I have about 4% error even with that small observational reaction error, right? You can see that's how the error is actually happening in real experiment. That's the missing part in this semester. So any simple error we observing, observational error added into the experimental observation, creating this final error. Okay. Let's check the independency of the mass really, because we expecting that. Let's reset this. Any question? Increase the mass into next value 0.571 by clicking the up arrow here, right? Whatever the next number, you may not see exact numbers as mine. That's okay. Nothing to worry. Just write it down there. And again, the same thing, change the angle, freeze it when the object start the motion, okay? Change the angle, keep the cursor on word freeze. Right there, okay, 29.9. So my error is consistent at least, okay? So I have error about 4%. It seems to be my error is consistent. So that's what you need to check. So the error is exactly the same because my two readings are very close to each other, okay? You can click and drag these, that will do the calculation automatically. So the error is about 4.5 now. Let's reset, increase the mass one more time, 0.633, and then click on change angle. And wait until it is start in the motion. You have to click as soon as it break the stability, okay? About 30. So my error is actually increasing now, not good. So my error gonna be now a little bit larger, 4.9. Click reset, increase the mass to next number, 0.701. Nothing to do with the mass, okay? It's only just our observational error. This number change right here, slightly changing mu, nothing to do with the mass at all, okay? Click change angle. Click the cursor on top of the word freeze. 29.9. So I'm going backward now a little bit. So the error going to be slightly less now. It should be a little bit lower angle actually than the larger. Click reset. Let's try one more data point. No meaning, just retrying this again and again. 0.778. Change angle. Freeze it somewhere maybe like 10 to 15 degrees. Take a screenshot there. And that will show you very nicely. And this red arrow is the normal and the green arrow is the friction force, and the blue arrow is the weight, right? So all the vectors are there. Take the screenshot like that location. Then let's let it run. Freeze it 29.9. So there's no effect of the mass of the object at all. Okay, that's what we observe there. Let me include that last figure right here. Those should go to your procedure section. Okay, those three. Double click. This should go in. It should go into your procedure section. Okay, all of these three. Okay, so this you can say, what's a good name for that one? This should be now, this is figure 2, earlier one. This should be then figure 3. Figure 3, simulator for friction with inclined plane. Okay, so those three figures should go to a procedure section, and all the graphs and data tables should go to the data section, and then all the functions, if you want, I see you guys doing slightly differently each other, that's totally fine. So these function you can include just beside the table in the table section, that's okay. I think I saw some of you doing, or you can collect everything into appendix C and then call them in your discussion part. That also fine. But don't just put all the function into the discussion, because I see very rarely, I think not many, very few just doing like almost the discussion look like just the set of function. That's not a discussion, okay? That's not the discussion at all. Discussion is not just putting the set of function there. You have to write in words and sentences about the results, about the errors, about the experiment in your own words. Calling function is okay to tell how you did that, but if it is just telling how you calculate everything in the discussion, that is not the discussion at all. Okay, so any question? All right, then I think what we should do maybe one question. We have about 20 minutes, maybe, yeah, more than 20 minutes, good enough time. So let's start one question on last chapter, okay? Let me quickly unshare this one and then reshare with the notepad to write, okay?